All right, in this set of problems, I'll be going through a combination of force diagrams and the equations. It'll be helpful if you have near you the list of equations that I'm going to be giving you, because I'll just sort of be writing them out. You're not expected to know the equations. I'll be giving them to you on the test, but you do need to know how to use them, and you need to know when the different types of forces apply and things like that. And so, you know, it's good to have that little exploring force types sheet nearby so that you can look and get the equations off of it and try and determine what sorts of forces are present as we're doing it. So this first problem here, I guess generally speaking, I should say there are sort of 3 steps we're going to go through when we do this. So step number 1 is going to be to make an FBD, which is just a force diagram or a free body diagram. All right. The second thing is going to be to put in the forces that you know. Add in like the numbers that you know, or that would be easy to find. Okay, and then the last thing you're going to do is you're going to use the balanced forces to figure out the things that you don't know. So generally speaking, you know, have this process in mind as we go through, because that's what we're going to be doing the whole time. All right, so we'll be kind of doing those 3 steps. This first one here, what we've got is we've got a magnet is being pulled up. A paper clip that's being pulled up by this magnet, but a string is holding it down. It's sort of taped onto a table. And so we have to think about what different forces might be acting on the paper clip. So the first step, we're going to make an FBD for this. You have to think about some different things. One type of force that's on this is gravity. Gravity's on pretty much everything that we do here, as long as it's not, you know, in outer space or something like that. We're going to assume it's on the surface of the Earth. So Fg on the paper clip, right, by the Earth. Then another force we've got here, the magnetic force is up. All right, we know it's up because the magnet is above the paper clip and it's going to be attracted to it. So magnetic force on the paper clip by the magnet. All right, and then the only other force that we have is tension. Tension is always in the direction of the string or the rope or whatever it is. So in this case, it's pulling the paper clip down. All right, Ft on the paper clip, and then it's taped to it's tied to a table. The string on the other end is connected to a table, and so I'm going to use table as the other object. You could use string as your object here, but I like, when I do a tension force, to have the 2 objects that are connected by the rope or the string. So now we have to ask ourselves, what sort of information do we know? There's a couple things that are given to you in the problem. One, it says it's a 1 gram paper clip. The other thing, it says we've got a magnetic force of 0.5 newtons. So we can use that information to try and fill in some of these forces here. When we say we have a 1 gram paper clip, we're giving the mass, all right? And then why that's helpful is because the mass is related to the gravitational force. Generally speaking, we did a lab where we saw that the gravitational force was equal to approximately 10 times the mass of an object if the mass was in kilograms, all right? So this has to be in kilograms here if we use this rule. So if we get a mass in kilograms, we multiply it by 10, and then we get the gravitational force. So on this first problem, the mass is 1 gram. We have to get that to kilograms, so 0.001 kilograms. All right, if you are confused by that process, go back, look at my metric mania key where I talk about metric conversions, and you can figure that out. But converting 1 gram to kilograms is 0.001 kilograms. And so then what we're going to do is we're going to multiply that by 10, all right? So 0.001 times 10 to get to the force, and we get 0.01 newtons as the force, all right? So our gravitational force is 0.01. And that is in newtons. So that's one thing we have. The other thing is it just tells us directly the magnetic force is 0.5 newtons. All right, and then what we're going to do is we're going to take advantage of the fact that we know that the forces are balanced on this paperclip. We know that because the paperclip is stationary. It's just kind of levitating here, floating in space, but it's not moving, so its forces are going to be balanced. That means all the upward forces need to equal all the downward forces. The only force that we have in the upward direction is the magnetic force. That's 0.5. In the downward direction, we have gravity and tension. Together, those have to add up to be 0.5. And so if you think about it then, the remainder of that 0.5 going downward needs to come from the tension force. Generally speaking, what we're doing in our head is we're saying, all right, 0.5 minus 0.01, and you get 0.49, all right, 0.49. All right, but now you can see the reason that we did that was because it means that the downward force together equals 0.5 newtons, and the upward force altogether equals 0.5 newtons. And so this one didn't ask us anything in addition to this. It was just making the force diagram. That one's kind of done. This next problem, we've got a box that's placed on a spring. There's no picture here, so sometimes if you want to like draw a picture to try and help you think about what's going on here, we've just got a box sitting here on a spring. It's compressed the spring. The box is 20 kilograms. All right, and so when we think about this, then we have to think about what forces are acting on the box. Gravity is, as I said, going to be on almost every one. So there's a gravitational force. It's on the box. It's by the Earth. All right, it's going in the downward direction. The thing that's going in the upward direction, that's the spring force. Spring, and it's on the box by the spring. Now, on this one, you might think of this as a normal force, but don't do that. If you've got a spring pushing against an object, it's a spring force. No normal force involved. It's just a special sort of case. And so if you've got a spring involved, spring force, not normal. And so this is all we have here. They're going to be equal to one another because there's only one up and one down. All right. The gravitational force we can get because we have the mass again. So gravitational force equals mass times 10. The mass is 20 kilograms. That's given to you up here. So we take that and multiply it by 10, and we get the gravitational force is 200 newtons. Because it's balanced, we know then that the spring force is also 200 newtons. All right, and then we look at what it's asking us here. It says, what's the spring constant for the spring? Well, you need to be familiar with the equations to understand what this is asking. The spring equation, or the elastic force equation, says this. Force of the spring equals kx. K in this case is the spring constant, and x is the distance that the string is stretched. All right? The spring constant is normally given in newtons per meter. All right? And so this is one of those cases where we need to make sure that everything is in the right units. So solving this for k, we get k equals the spring force divided by the distance stretched or compressed. In this case, it's actually compressed because there's a box pushing down on it. Spring force we said was 200 newtons. All right, now this x should be in meters technically. Like if we're going to plug things into equations, distances always need to be in meters. So instead of centimeters, I'm going to call it 0.025 meters. All right. 200 divided by 0.025, you should get 8,000. And that's newtons per meter. All right, now you could have called this 80 newtons per centimeter, but I think that this is a superior answer. So 8,000 newtons per meter is more normally what a spring constant is given in. So that is that. For number 3, it says a child is holding a soccer ball underwater by pushing it straight down on it. Soccer ball has a mass of 0.43 kilograms. The volume is 5,500 centimeters cubed. What force is required to keep the ball down? The soccer ball is the object of interest. The density of water is 1,000 kilograms per meter cubed. Alrighty, so this one, there's water, there's something being held underwater. That should scream out to you that we're talking about a buoyant force, because if you've got an object and it's submerged in a fluid, that's the buoyant force. Buoyant force opposes gravity, so it's always in the upward direction. So F B. In this case, the object of interest is our soccer ball. And the thing that's putting that buoyant force on it is the water. All right. Of course, we have gravity on this one, all right, because gravity's on pretty much all of them. Fg on the soccer ball by the Earth. And then, additionally, we've got this child pushing down on the soccer ball. When you're pushing on something with your hands, it's a normal force. All right, so normal force on the soccer ball coming from the child. The question is, how big is this force going down? So we have to figure that out. We got to think about some different forces that we've got. The first thing it says is the soccer ball has a mass of 0.43 kilograms. So that immediately lets us fill in this 0.43 times 10. So it's 4.3 newtons. Okay, now the two other forces are unknown here. We know that the normal force is going to be our final answer though, because the question was what force is required to keep the soccer ball down. So probably the buoyant force is what we're going to calculate next. And you can see if you look at the buoyant force equation that we have all of the things that we need to calculate what the buoyant force is. Because it's force buoyant equals gravity times the density of the fluid times the volume of the fluid. All right, and in this case, that's equal to 10 times 1,000, all right, which I gave you there. Gravity, by the way, that little g is always 10 newtons per kilogram on Earth. It's the same one that we use when we calculate the gravitational force from the kilogram's mass. So 10 newtons per kilogram is what that is, times 1,000 kilograms per meter cubed, and then the volume here. This one, actually let me go through and talk about this really quick. 5,500 centimeters cubed. If we're getting that into meters cubed, we have to convert from centimeters to meters, but it's cubed, all right, which means centimeters times centimeters times centimeters, which means we have to convert it 3 times, all right, because it's a 3-dimensional unit. And so normally if you were looking at the metric prefix system, King Henry died by drinking chocolate milk. All right, and you were going from the base, from centi to the base unit, you'd be jumping over 2 spots to the left. But as I said, this is cubed, so we have to do the conversion 3 different times. So we jump 2 spots to the left, that handles 1 of the centimeters, 2 spots to the left again, handles the 2nd centimeters, 2 spots to the left again, handles the 3rd set of centimeters. All right, and we end up with 0.0055 meters cubed. All right, so this needs to be in meters cubed. Get used to doing the centimeters cubed to meters cubed conversion. I'm not going to give you a whole lot of conversions like this where you'd have to go from a unit cubed to another unit cubed, but centimeters cubed to meters cubed is going to come up a lot, and so I want you to be comfortable doing that one. So going back to this buoyancy equation, that is the volume. Cut off a little bit of the bottom here. Alrighty. So 10 times 1,000, I'm just actually going to rewrite that really quick. 10 times 1,000, and then the volume here we said was 0.0055. So if you multiply that all out, you should get something like 55 newtons. So that tells you that the buoyant force is 55. Then, because the forces are balanced, we know what this normal force needs to be, all right? Because if you add the upward forces, it needs to be balanced. The upward force is 55, so the downward forces need to add together to be 55 as well. So we take 55 minus 4.3, and we get 50.7 newtons downward, all right? And that is our answer, 50.7 newtons. Problem number 4. A person is pushing a 20-kilogram box at a constant velocity across a rug with a horizontal force of 150 newtons. What is the coefficient of friction between the box and the rug? The box is the object of interest. So on this one, we've got, this is like a classic sort of problem, right? We've got a box is being pushed across a rug. There's going to be some friction here because a box across a rug, it should, in your mind, think that there's some resistance there to the motion. And so when we draw our FBD, there's the gravitational force, Fg. All right, this is on the box by the Earth. And it's a 20 kilogram box, so we know it's 200 newtons. All right, additionally, there's a normal force between the rug and the box because it's pressing down on it, all right? There are two surfaces pressing together between the rug and the box. So there's F normal here on the box by the rug. All right, and that's also got to be 200 newtons because it has to balance out with the gravitational force. Technically speaking, maybe you should have all of the forces drawn in before you do this balance thing, but the other two forces are in the horizontal direction, so that's kind of all we had for vertical there. In the horizontal direction, we've got this person pushing it with 150 newtons of force. That's a normal force. Again, also, whenever we're pushing something with our hands, it's a normal force. So this is on the block by the person. All right, that equals 150 newtons. And then there's the friction force that's going to resist its motion. And this is on the box by the rug. All right, that also has to equal 150 newtons. So we've got all the forces on here, and it's just asking us for the friction coefficient. So we have to go to the friction equation. Friction equals mu times, oops, that should say FFR, equals mu times the normal force okay, and in this case, what we're looking for is mu, so mu equals FFR divided by the normal force. Some of you might be looking at this and saying, okay, there are two normal forces. Which one do I use? Well, the friction force we're interested in is between the box and the rug. So the normal force that we need to look at is the one that's between the box and the rug. That's the upward one. All right, so we're looking at a box and rug interaction here for the friction force, so we need the box and rug interaction for the normal force. So friction was 150. The normal force was 200. 150 divided by 200 is 0.75. There are no units on a friction coefficient, so nothing else there. This next problem is a little weird because we don't deal with charged objects very often in our lives, and so it's a little strange to see how it works, but this is what we've got here. We've got some negatively charged object, and we've got a positively charged sphere. And if you're not familiar with this already, you should become familiar with it, but if they're opposite charges, they're going to attract one another. So this sphere is going to be pulled upward towards this other negatively charged object because a positive and a negative attract one another. That's the only significance of the sign on the charges. So just think about, is this attractive or is this repulsive? And then other than that, just forget about the sign. So it's going to be an attractive force, therefore the sphere is going to be pulled up by whatever that other object is. If both of them were positive or if both of them were negative, it'd be a repulsive force, and then the sphere would be pushed down by whatever that other object is. All right, so it's sitting here and it's levitating above the ground. All right, so it's just up in the air levitating there. What we've got here is we've got two forces acting on this object. There's the force of gravity, Fg, on the sphere by the Earth. All right, and then we've got an electrical force, Fe, on the sphere by whatever that other object is. All right, and that's it. All right, that's all that's acting here. They're going to be equal to each other because they're the only two forces on that object, and it needs to be balanced. So if you look at this, the question here is, what is the mass? If you don't know the mass, it should make sense that we probably aren't going to be able to figure out gravity right away. So what we're going to do is we're going to focus on the electrical part of this. all right, and try and figure out what the electrical force is. So we say electrical force, based on the equation that you have, is equal to K times Q1 times Q2 over R squared. All right. That is 9 times 10 to the 9th. All right. And then the charge is given in microcoulombs. The reason I always give it to you in microcoulombs is because that's a normal unit in science for charge. Unfortunately, a unit of, like, if we had a coulomb of charge, that's just an incredibly large amount of charge. So we don't ever give charges in coulombs. It's always in these microcoulombs. But microcoulombs are really, really small, and then they create this problem when we put them in the equation. A microcoulomb is 1/1,000,000th of a coulomb, all right, or is 10 to the negative 6th. So what we do is we plug this in. You have to have 25 times 10 to the negative 6th, all right, for a microcoulomb, all right, and then the other one is 100 microcoulombs, so 100 times 10 to the negative 6th, all right, and that's in there, and it's over the radius squared. Luckily, this one is in meters, so we don't have to convert that one. It's 0.671 meters, all right, and then we have to square that. If you plug that into your calculator, you should get something that's around 50. It's something like 49.97 or something like that, but I think that 50 is close enough. So I'm going to say it's just about 50 newtons. All right. And then if we're thinking about it, we want to get the gravitational force. All right. If this is 50 newtons, the gravitational force is going to be 50 newtons as well. And then we can get the mass, because mass times 10 equals the gravitational force, or mass is going to equal the gravitational force divided by 10, all right, which equals 5 newtons. Oh, 5 kilograms, sorry. And that is that. Okay, on to these last problems on the back. First one here, we've got another buoyancy problem because there's a ball and it's placed underwater. This time it's attached to a spring. So what we've got is we've got kind of the bottom of a pond here, and attached to that is a spring, and then there's a ball attached to that spring. I'm going to draw that a little bit better. All right, and it's underwater. All right, and so the ball is being pushed up by the buoyant force. The spring is pulling the ball down. Gravity, even underwater, I mean, gravity's still having an effect, so gravity is also pulling it down. So the forces that we have on here, we have Fg on the ball by the Earth. We also have F spring, which is an elastic force on the ball by the spring. Right. And then the buoyancy force is upward, Fb on the ball by the water. Things we know here, it's a 4 kilogram ball, so that means the gravitational force is equal to 40 newtons. All right. Spring, we don't know, and it's asking about the spring, right? It says how far will the spring be stretched. So if it's asking you about something as like the final answer, is probably not going to figure out spring right away. So we're going to work on this buoyant force next then. You know that the buoyant force is equal to G times the density of the fluid times the volume, okay, which in this case is 10 times the density of fluid, 1050. All right, and I've given you the volume this time, 0.01. All right, I've given it to you in meters cubed, so you don't have to do that conversion. So that's all pretty nice. If you multiply those together, you should get 105 newtons. So buoyant force here, 105 newtons. Now we know, if we're looking at these and considering the fact that they're balanced, that the spring force needs to be 65 newtons. All right. And then it's asking how far the spring has been stretched. So over here on the side, we can do the spring equation. We know that FSP equals Kx, all right? Spring constant times how far it's stretched. We want to know how far it's stretched, so we'll solve for x here. X is going to equal the spring force divided by the spring constant, which in this case is equal to 65 divided by 2,000. And if you do that, you should get 0.0325 meters. All right, which is equal to 3.25 centimeters. Okay. Continuing on here, we have a problem. This one there is kind of confusing. There's a spring is pushing against a board. The board is being pressed against a wall. And the question is, how much compression must we have in the spring so that the block doesn't slip? And so this one's related to spring force and it's related to the frictional force as well. So there's quite a bit going on here. The first thing to do every time, make your FBD. All right, so we've got going down, we've got Fg, the gravitational force on the block by the Earth. Upward, you have to think hard about what would be keeping this up. The block wants to slide down. The only thing that's going to be keeping it up is a friction force that exists as it wants to try and slide down that wall. And so this is actually the friction force up here on the block by the wall. Alrighty. Continuing on, the thing that's pushing it this way is going to be the spring. And then the thing that's pushing it back, you've got two surfaces pushing against each other, the block and the wall. Okay, that creates a normal force. So F normal on the block by the wall. All right, so those are those things. Now we look through and we see what information we know. We know the gravitational force is 2.7 newtons because the mass is 0.27 multiplied by 10. That means that the friction force also has to be 2.7 newtons. The question is here, how much does this normal force have to be so that the spring force, how much does the spring need to be compressed so that this frictional force would equal 2.7? And this is where it gets a little bit tricky. So we know the friction force has to be 2.7. All right, we know the coefficient of friction. If we know those things, then we've got two of the variables in this equation. Force of friction equals the coefficient of friction times the normal force. All right, so we know the friction force, we know the coefficient of friction. We can figure out what the normal force would be from this. Normal force is equal to the friction force divided by the coefficient of friction, which in this case just equals 2.7 divided by 0.46. Calculating that, you get the normal force equal to 5.89. Oh, sorry, 5.87. All right, if the normal force equals 5.87, then the spring force has to also equal 5.87. And then it's asking how far the spring needs to be compressed. So then on this one we say the forces of the spring equals kx. On this one, we know that the K for the spring is 120 newtons per meter, and we know the force on the spring is 5.87. So then we say 5.87 equals 120 times the distance it's compressed. All right, and then solving there for x, or the distance compressed, we get 0.489 meters. All right, and that's the final answer. That one was tough, lots of steps in that one, so yeah, that one's probably the hardest one on here, I think. This next one, it says a semi-trailer truck is required to stop for inspection on an interstate highway to make sure it's not carrying too much weight. The maximum allowable weight on a semi is 80,000 pounds. The semi's weight is calculated based on its compression of several springs on a giant scale. If a semi is atop a scale which has 20 uniform springs, K equals 2 million newtons per meter, and the springs are compressed by a distance of 1 centimeter, does it fall within the weight requirements? So this one, lots of words there. But what we're looking at here is we've got 20 springs, and we just have to figure out, first of all, how much force there is for each spring. And so what I'm going to do is, essentially, if you condense all the springs to one spring force, it makes it a little bit easier. So the only thing really holding this up, if you think about it this way, is like FSP. And I know this is kind of simplifying it because there's also that block there, all right? And so, but I think this is an easier way of thinking about it. The springs are holding the semi-trailer up, all right? So FSP there, and then gravity is pulling the semi-trailer down, all right? And those are kind of, essentially speaking, if you simplify it, the only two forces that are acting on this semi-trailer. And so what we have to do is we have to figure out what this FSP is so that we can try and figure out what the mass or the weight of the truck is. The spring force is equal to K times X, the spring constant times the distance. All right, and in this case, that's 2 million times the distance it's compressed, 0.01 meters. It was given in centimeters, but you have to get it to meters. So if we do this, you should get 20,000 there. Now, that's just for one spring, all right? So for all springs, we need to multiply that by 20. All right, because it said there were 20 springs here. Each of them has a 20,000 Newton force on it. All right, and you get 400,000. So all of the springs together pushing up on the truck have 400,000 newtons of force. All right, that means the gravitational force on this one is equal to 400,000 newtons. All right, and then we can use that to figure out what the mass of the truck is. The mass is equal to the gravitational force divided by 10, which ends up giving you 40,000 kilograms. All right, then we have to convert that to pounds. All right, you multiply by 2.2, and you should see that this equals 88,000 pounds. Which means that it is too heavy. Okay, last problem here. We've got a box that's being, again, dragged, so you should think there's some friction here. There's also a spring force acting. This one actually quite a bit simpler than the other two, even though it seems sort of complicated. So first we start by making our FBD again, just like normal. We've got the spring pulling the object, FSP, on the block, or box, in this case by the spring. Okay, so in this case the spring is pulling it. Then we have the gravitational force downward, of course, Fg on the box by the earth. Then we have the normal force upward, Fn on the box by the road. Right? And then we have a frictional force here because it's being dragged. So this is Fr on the box by the road. Going through here, trying to fill in what we can. We're trying to find the mass of the box. So again, we don't know the gravitational force. It'll probably be the last thing that we find. But we can think about some other things here. So it says the string is stretched by 2 centimeters, all right, and we know the spring constant. So we can figure out what the spring force is going to be. All right, so that's the first thing that we can start with. Spring force here is equal to Kx, all right, which equals 3,000 newtons per meter times 0.02 meters, because we have to go from centimeters into meters. When you do that, you should get 60. So this gives us the spring force that's equal to 60 newtons. That means that the friction force here is also equal to 60 newtons. Going on, the normal force, the way we're going to find that is by using the friction equation. We know that the force of friction is equal to the mu, the friction coefficient, times the normal force. All right. What we're looking for here is the normal force. So that means normal force is going to equal the frictional force divided by the normal force. Oh, sorry, by mu. All right, which in this case is going to equal 60 divided by 5.3. From this, we get that the normal force equals 11.3 newtons. From that, we know that the gravitational force has to equal the same because normal and gravitational are equal to each other. So Fg then equals 11.3 newtons. And from there, we can get the mass because the mass is equal to the gravitational force divided by 10. All right, so it's 1.13 kilograms. Okay, I know that was a lot. This video is almost 40 minutes long, so thanks for sticking with me if you watched the whole thing. We're going to do some more practice with some of these things, but just, try and make sure you have the best understanding possible of these. If you have questions, please bring them in, and we'll get you sorted out. So, take care.